Let's go to page 95 in your textbook. Page 95. So today we're going to look at relative velocities. That's not how fast your dad drives. Little joke there. You like that one? No? Relative velocities. I always like teaching this because of the guy that wrote this book is kind of wacky. Tarzan and Tarzana. You've probably heard of Tarzan. Tarzan and Tarzana are brawny 8 people. That's what it says. Decide to have a race across the river. Both are excellent swimmers and have the same ability. Tarzan swims straight across, landing on shore directly across where he started. Tarzan jumps in and points herself across the river, but ends up farther downstream when she reaches the other side. The two are pictured in figure 324, which are not up there. In fact, I think that's why I had that blank page to start, right? Yeah, it is. Okay, so this is like page 95 here. So you got these two brawny 8 people. I don't know why they have to be brawny, and I don't know what 8 people means. Does it mean they're raised by 8, so they're like, you know, father was an 8, mother was a human? I don't know what that means. It's kind of weird, right? Okay, so Tarzan, and it should be easier if they didn't have the same first letter of their names, but Tarzan decides to swim straight across. Right? And to do that, because the river is downstream, he has to swim this way, right? And this is the current, and you would call this the result, right? Right? Remember this kind of stuff in grade 11? Tarzana, she decides to. Okay, you're welcome. Okay, so Tarzana, she just jumps in and starts swimming, but because of the current, she ends up where? Downstream. Okay? Downstream. Who finished first? Who got to the other side first? Can you tell? Who went farther? She did. She went farther. She went along the hypotenuse. She went straight across. So if she went farther, did she go slower? Did she get there first? Not sure, are you? I always get to this point and I go, you know what, I don't remember either.
She got there first.
We'll figure it out. Okay, then there was, stay with me here, then there was Cheetah, faithful brawny 8 pet. Now I have no idea what species he is. He's also brawny. He's an 8 pet. Is he an 8? Is he like a dog that's raised by 8? And why is his name Cheetah if he's an 8? This is Tarzan here, this is Tarzana. Anyways, I don't know. The guy writing this, faithful brawny, he chose to swim across the same river by the time when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana swam it. Cheetah too is a good swimmer and has the same ability as Tarzan and Tarzana. In other words, he can swim just as fast in no current. The Cheetah finished the crossing in a shorter time. So Cheetah's looks like this, right? He swims across, but because the current is 5 times, he ends up way down there. Did he get there faster? All of this is known as relative motion. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road, as shown in figure 325. The patrolman will measure your velocity relative to his position. In this case, the patrolman is not moving. Let's assume the velocity he measures is 140. Your velocity is said to be 140 kilometers an hour measured relative to the ground. Flip the page over, and you'll see the cop car there. Like so, right? And here's your car. And you go blazing past at 140. Well, because he's stationary, he measures your speed at 140, right? See that there on the next page? Someone did a bad job in his textbook layout because I wish the picture was on the same page. I hate that. Last paragraph on the bottom of page 95. Now suppose you pass the patrol car with a velocity of 140 while it's moving with a velocity of 100. First of all, that's a bad idea. If the cop's doing 100 kilometers down the road and you pass him doing 140, you get exactly what you deserve. I was in a car once that passed a police car. We got pulled over. He was doing 95, we were doing 95 and a half. He pulled us over. Said we were speeding. It took us about 2 minutes to pass him. It's kind of awkward. I'm sitting there on the passenger side kind of looking at him. Very awkward. So, what is your speed relative to the police car if you're doing this, right? I'll do it sideways here. If he's doing 100 and you're doing 140, what's your relative velocity? Well, it's only plus 40, right? Because it's relative to his speed, kind of thing. What if you were doing 140? It's not in the book, but what if you were doing 140 and he's over here doing 100, but he's going towards you? What's your relative velocity? 240. Right? He's closing at a speed of 240 kilometers an hour. Okay. Notice that your velocity is the same, but the two measurements done by the patrolman are different. The bottom line is that a velocity value is measured relative to a reference frame. We talked about reference frame in grade 11. Right, Dylan? Listen, Matt. Here's the learning part. Doesn't add up.
No, like that. You are crashing each other like that.
It's if you crash into each other like that, it would be like you traveling at 240. It would. No? Why do you say no?
There's a Mythbuster guy.
I've seen that one, that Mythbusters one. We should watch it.
Yeah, watch it.
We'll find it later. I'll find it. I gotta do this. We'll find it. Maybe I'm wrong. In everyday use, we are accustomed to using the ground as a stationary reference frame. This frame is implied in most problem situations. Okay, let's just skip all that. Now, on page 96, there's a whole bunch of the worst physics mumbo jumbo I have ever seen in my entire life. It is quite possibly the worst bit of textbook writing ever. B-O-G, B-M-G, B-O-M, oh my God. B-O-M-G is what it should be. Right? Here's what, it's probably written in the side of the book there for you. Is it? They got V-R, and I've got V-C and V-W. Have you got that written there on page 96? Yeah? Okay, so VR would be like resultant velocity. VC would be like velocity of current in a river. VW would be like V wind. Wind and current are kind of the same things, right? And then you might have like VP for planes. I guess the planes are in the wind. This one should go over here. And you might have VB for boats, right? Okay, all still too much. Let's make it simple. Resultant is plane plus wind, right? Remember that? Or if it's a boat, resultant is boat plus current. That's simple, easy to understand. These are all vectors. Right? And if we have to do vector subtraction, just going to make myself some more room here. If I have to do vector subtraction, if it's boat, well, that's going to be resultant minus current. And if I have to solve for the current, well, that's going to be resultant minus boat. And when I say minus, I mean vector subtraction, right? The stuff we did yesterday, right? Not just like the numbers subtract each other. Don't do that. And the same is true for planes and winds. Okay, let's skip right to example 7. Relative velocity, relative motion in one dimension. So simple, it's probably not worth even talking about.
Apparently, Tarzana is Spock.
She's Spock.
Well, you look at the pictures, and that's Tarzana.
I guess, okay. No. Page 97. In one dimension, the river problem has 3 possible cases shown in figure 326. When the river flows, its velocity is 1 meter per second east. Tarzana can swim at 2 meters per second in still water. So case 1, she's swimming no current, right? So what's the resultant here? Right? Well, it's going to be 2 plus 0. I'll just put a dot there. Right? So what's the resultant? Well, 2 meters per second. There is no current to add. 2 meters per second. Right? Easy. Review. If she's swimming with the current, well, then the resultant's going to be 2 plus 1. And the resultant is 3 meters per second. When you're flying in a plane, Monique, and you're flying with the wind, I was going to say you don't use much fuel, but you, gliders, right? Don't use fuel. Oh, for a steady flying plane. Okay, so when you're flying with the plane, do you use much gas? Yeah, but you're using less, right? Because you're with the wind, right? And in fact, you would probably fly faster, right? Case number 3, against the current, what's the resultant going to be? It's going to be 2, right, plus 1 the other way. So what's the resultant? It's going to be 1 meter per second. You can all do that in your head, right? Easy stuff. There's no direction there involved. You've been given no direction. Okay, so that's all shown, like, that's on page 97 and 98, and again, they make it way more complicated than these. Far more complicated. The real trick is when we get into two-dimensional relative velocity. And you guys did this last year in grade 11, right? And we did it by Pythagoras, and we did all that kind of stuff. So we're going to do example number 8, bottom of page 99. All I did up here, this was all one-dimensional relative velocity, right? One-dimensional, forward, backward, easy, right? Child's play. Oh, I don't know. You don't have the case 1, case 2, case 3? Oh, sorry. Sorry, man. You know what, just print this out later. Just watch. I'm going to do example number 8 now. Example number 8 is on page 99. Okay? Again, you guys know how to do head to tail stuff. So case 1, assume Tarzan can swim at 2 meters per second. The current is 1 meter per second east. Tarzan is seen to swim directly across. Seen to swim. So it's code for the resultant, right? He swims at 2 meters per second. The current is 1 meter per second east. Tarzan is seen to swim directly across. He's going this way. Here's the current. There's the result. How do I know the resultant is straight across? He's seen to swim directly across. Okay? And what are we to find here? We are to find the resultant velocity, I believe, right? Find the final velocity of each one. So, he's swimming at 2. The current is 1. We want to know this one. Now, quite often, especially in grade 11, the resultant was the hypotenuse of the triangle, right? But it's not here, is it? Takes a little bit of figuring out to draw the picture. So how am I going to do this one? How am I going to set it up? Is it a right triangle, first of all? It is. So in this case here, you're going to have like 2 squared is equal to 1 squared plus r squared, right? These are the sides, right? And the hypotenuse is the 2. It's the one that's by itself. So you're going to have 2 squared, oh, don't do that. You're going to have 4 is equal to 1 plus r squared. Take the one to the other side. 3 equals r squared. R equals square root 3. Somebody find the calculator that doesn't work, right, Alex?
Yeah, exactly.
1.73. How come he's going slower than his original 2? He's got to use up some energy going against the current, right? That makes sense? Do I need an angle here? No, because we know, we're told he's going straight north. Straight north. Case number 2, she swims at 2 meters per second. The current is 1 meter per second east. She's seen to direct her body directly across. In other words, she just aims straight across and lets the current push her downstream, right? Like this picture here. Let's draw out the picture. Tarzana. Current. Resultant. So in this case here, this is our 2, this is our 1, and this is our r. Because the hypotenuse is the r, now it's r squared equals 2 squared plus 1 squared. She's going to be going faster, isn't she? Hopefully you can do this math in your head. 2 squared is 4, 1 squared is 1, square root 5, right? I'm hoping you can do that. 2.2. What card? 2.2 meters per second. Is she traveling faster? She is, but she went farther though, didn't she? Right? So we still don't know. We still don't know. Case 3 is old Cheetah, the Brownie Faithful 8 pet. Always makes me laugh. How about you guys try this one on your own? What do you give me that head shake for? Is this any different than case 2? Exactly the same as case 2, except now the current isn't 1, the current is 5. Go ahead and try case 3, I'll be right back. So what's this look like? He swims, and again we got problems here because they use the same letters. So big C Cheetah swims at 2, current is 5. That's your resultant, right? Cheetah swims like Tarzana, pointing directly. Oh, I gotta fix that sheet. Holy moly, it's bad. My apologies. I apologize. That's bad. Bad teaching. So this is going to be r squared is equal to 2 squared plus 5 squared. Right? R equals 4 plus 25, the square root of that. So r is going to be the square root of 29. A little over 5. 5.4. Cheetah's cooking. He's moving fast. But again, which one gets to the other side first? Well, the answer will be revealed right away. Flip the page over, if you're following along. Top of page 101. Whoa, now hang on here. Is this done? This one's not done, is it? In fact, I got to do this, right? Remember doing this stuff? Opposite over adjacent. Opposite is... Yeah, we should have done it with Tarzana, right? 5 over 2. No, because we know he went straight across. No, we don't, but it asks for the result, so. So this one is inverse tan of 5 over 2. $68. So that's going to be north, 68 east, right? North 68 east. You can do the same thing for Tarzana. I'm not going to bother. I want to get right to the good stuff. North 68 east. Okay, so who got there first? Well, if you read on the top of page 101, finding the time to cross. So who finishes first in this race? To find out, we need to look at the 3 vector diagrams shown together in figure 335. So they are, I'll just do them quick, right? They're like this, right? Tarzan is like this. Tarzana is like this. And Cheetah, he's like this. Okay? The equation v equals d over t, rearranged to find times, becomes time equals distance over velocity. We now needed to find out which v to use. If you look at the diagrams in figure 335, the velocity of the points in the direction of the desired motion, north, is the appropriate choice. So whichever has the greatest speed across. Well, this guy, Tarzan, he's going at, was it 1.8 or 1.7? You guys aren't paying attention back there, I can tell. 1.73. He's going at 1.73. His component that's north is 1.73. Tarzana, her component straight across is 2. Cheetah's, his component straight across is also 2. So in fact, who are the winners?
Oh, the handout says everyone went 2, so no.
What?
Yeah. Tarzan swims at 2. Tarzana swims at 2.
Let me see that. No. Tarzan swims at 2 at an angle.
Okay.
His velocity straight across is only 1.7. Okay. So these two actually tie. Cheetah, he just ends up way downstream, but he gets there in the same amount of time. Okay. And we're still not sure what he is, yes. Whether he's an ape or a pet or what he is. Yes. I don't know. Okay. Let's have a look at number 9 here. I'm almost done. Now, once again, the textbook is screwed up. I've become quite critical of textbooks. You will find as you go through your university career that there will be mistakes in textbooks as well. And probably the only reason I continue to point this out is to point out that textbooks make mistakes. When I wrote part of a textbook, I made mistakes, and they're still in there. It's very frustrating. The textbook company also added mistakes in that I didn't have. Anyways, pilot with a heading of north 30 east and an airspeed of 400 kilometers flies into a wind coming from the north at 110. What is the plane's velocity relative to the ground, and how long would it take to complete a journey of 1,000 kilometers at north 30 east? Okay, now, there's a problem here. Okay? The pilot is heading at north 30 east. North 30 east. And the airspeed is 400. Coming from the north at 110, right? From the north, so the wind is taking us this way, right? So my resultant is going to be this way. It says, how long would it take to complete a journey of 1,000 kilometers an hour at north 30 east? Is this plane going to go north 30 east? No. Completely wrong. Someone in the textbook editing department threw something in there, or the guy that wrote it didn't do the answer key or something. There's a mistake there. So what should it say? At his current direction or exactly, right? It should say, how long would it take and at what direction should he go, is what it should say. Plane, wind, result. And I only really leave that in there just to point out that there are always mistakes in textbooks. Okay, so here's an example. We've done vector addition by components. Here's one, an actual word problem. That's the last one we're going to do, I think. There's no example 10, is there? No. Okay, so I'm going to do this, then I'm going to give you some time to work. What are the steps to vector addition? First thing, Ryan, hello. First thing is to break it into x and y components, right? So we're going to draw our north 30 east. North 30 east. And it's an airspeed of 400. So it looks like that. I'm going to label this px, and I'm going to label that one py. Plane x, plane y. Px is going to equal its opposite, so we're going to use sine 400 sine 30. I should put some arrowheads on here. $200 to the right, so it's going to be positive. Py then is going to be 400 cos 30. $346. Will these two numbers ever add up numerically to this number? Like, will it ever be like 200 and 100? And they shouldn't be. Okay. What's the next step? You got to break the other vector into components, right? You're in luck here because the wind is going from the north, so it's to the south, right? So does it have an x and y component? It does not. If you want to write wind x equals 0, you go right ahead. The x component of the wind is 0. What's the y component? Minus 110. Why minus? Because it's south. See how I lined up my x's here and lined up my y's? Makes it sort of easy, 2 columns for adding. Organizes it nice. So resultant x is going to be 200 plus 0, 200. Resultant y is going to be 346.4 plus negative 110, which is 236.4. So I've added my x's, I've added my y's. Now what am I going to do? Put them back together, right? Take them apart, add them together, put them back together again. My Rx is 200, so that's going to be 200 to the right. This is Ry is 236.4, that's up. Giving me an overall resultant of that direction, which is exactly what I had sort of in the first place, right there. Is it for sure a right triangle? They're x and y components. R squared is going to be 200 squared plus 236.4 squared. I get 309.6. Let's just round it up to 310. Did you get 310? Am I done? Got to find the angle. $236.4 all over 200. I get 49.8. Let's just make it 50. That's going to be east 50 north, isn't it? That's the overall result. If you had to do that in grade 11, you would have had to have used protractor and ruler, right? Okay. Oh, how long would it take? So what did we do there? Yeah, it's just going to be, right? V equals d over t. We're traveling at 310. The distance is 1,000. Solve for time. 1,000 divided by 310. 3.2 hours. And you'd end up traveling at east 50 north. Okay, so you've got the second page has a whole bunch of questions. You probably got those questions in grade 11. You had to do them by protractor and ruler. You've got them now there. They're right there. I was just wondering about that. Give me like 5 seconds. Okay, so you can work on these. There's a whole bunch of questions there. There's a couple of subtraction ones at the bottom. How do you subtract vectors by components, Jake, with subtraction? Subtract the components instead of Add them. Answers are there. QR code to get to the solutions are right there. Have fun, my friends. How'd it turn out?
Can I go get a drink quick?
Sure.